Hi, this lesson is about rational functions. Rational functions are functions with at least one variable in the denominator, but it could also have variables in the numerator. To find the domain of a rational function, you must set the denominator equal to 0 and solve it. The solutions are actually the exclusions to the domain as long as those solutions are real numbers. So here's our first example. G of x equal to 2x over 5x minus 4 is a rational function. So we want to determine the domain, and so therefore we have to determine what values are excluded from the domain. In other words, when would this denominator equal 0? Because division by 0 is undefined. So you take that denominator, you set it equal to 0. 5x minus 4 is a linear function. So you add 4, divide by 5, you get that x is equal to 4/5. But remember, that's not a solution, that's an exclusion. So your domain is all real numbers except for 4/5. So the way you express that in interval notation is that it is the integral from negative infinity to 4/5 union from 4/5 to infinity. And both of those intervals, you need to have parentheses around them, not brackets. Because you do not want to include 4/5 in the domain, because at 4/5 it would be undefined. So here's another one. We're trying to figure out the domain of g of w, which is equal to -1 over w squared minus 9. So just like the last example, you take the denominator, set it equal to 0. This denominator is a quadratic equation. And that could be solved in one of two ways. Either you can factor it, or you can use the square root method, which is what I did. So first thing I did was I added 9. Then I took the square root of both sides, and the square root of 9 is plus or minus 3. So remember to put that plus or minus in front of the solution when you are using the square root method to solve a quadratic. So that means that -3 and +3 must be excluded or omitted from the domain. So this represents all real numbers except for -3 and 3. So you always write your domain from smallest to largest. So it's the set of numbers from negative infinity to -3, union from -3 to 3, union from 3 to infinity. So what that means is that -3 and 3 are not part of the domain, but all other real numbers are. All right, so here's another one. We have f of t equal to -t squared over t squared plus 4. All right, so again, I'm taking my denominator and I'm setting it equal to 0. And just like the last example, I'm going to solve it by the square root method. So subtract 4 first to get the t squared alone, then take the square root of both sides. But the square root of a negative number is an imaginary number. So when you solve this, you get plus or minus 2i. So since that is not a real number, there is no real number that would result in division by 0. And therefore, your domain is the set of all real numbers. There are no exclusions. Okay, so there's often exclusions to the domain of a rational function, but not always, like in this example 3. Another important attribute of rational functions are asymptotes. So an asymptote is a line that a graph approaches but never touches. We'll be talking about both vertical and horizontal asymptotes. But before we do, we need to understand what a limit is. So this is just a very short introduction to the concept of limits. So we use limits to find asymptotes. Limits allow us to analyze the behavior of a function as x approaches a number that may or may not be in the domain. So in most cases, it would not be in the domain, but there's different types of asymptotes, not just horizontal and vertical ones. So here's our notation. The limit as x approaches a of f of x equals L. So again, that's exactly what I just said. That's how you read that. And so what this is saying is, what is the behavior of f of x, which is y, as x gets closer and closer to some number that we're calling a? And if it equals some value, some finite number called L, then we can say that this limit exists. But with asymptotes, your limit is going to approach either plus or minus infinity, which we'll see in a few some examples later on when we're talking about vertical asymptotes. And when we're talking about horizontal asymptotes, we'll be actually able to identify what that L is. So vertical lines, which would be a vertical asymptote in this topic, are expressed in this form, x equal to some number, whatever that number may be. And horizontal lines in this topic, your horizontal line would be a horizontal asymptote that's expressed in this form, y equals b. Okay, so vertical asymptotes often, not always, often exist where the restrictions to the domain exist. In other words, where the values of x, where the denominator will equal 0. So if a is not in the domain of f of x, and as x approaches a, your f of x is approaching plus or minus infinity, then we can say that x equal to a is a vertical asymptote of f of x. With horizontal asymptotes, you have to look at the behavior of f of x as it approaches positive infinity and negative infinity. And if your function, as it approaches positive infinity or negative infinity, approaches some finite number that I'll call b here, then you can say that y equal to b is an asymptote. So in other words, the graph is getting really close to this value of b as the x values get very large or very small. To evaluate the limit, as x approaches positive or negative infinity, we determine the horizontal asymptotes of a rational function by following this table right here. And this is just a quick way to identify horizontal asymptotes. So f of x and g of x is your rational function, where f of x is the numerator and g of x is the denominator. So the first thing to consider is if f of x and g of x have the same degree, and remember the degree is the largest exponent. So if the largest exponent in the numerator and the denominator are the same, then your horizontal asymptote will be the ratio of the leading coefficients. Remember, a leading coefficient is the number in front of the term that determines the degree. And the ratio means that you're getting the leading coefficient from f of x divided by the leading coefficient of g of x. So the ratio will be a fraction. So here's an example, example 1. The degrees are the same. It's a third degree polynomial in the numerator, third degree polynomial in the denominator. It doesn't matter how many terms that polynomial has, it matters that their degree is the same. So what this statement says is that I take the ratio of the leading coefficients. The leading coefficient in the numerator would be 2, the number in front of x cubed, and the leading coefficient in the denominator would be 6, the number in front of x cubed. And so the ratio is 2 over 6, which reduces to 1/3. So y equal to 1/3 is a horizontal asymptote of that function, of that rational function. Okay, here's our second scenario. So if the degree of f of x is less than the degree of g of x, in other words, if the degree in the numerator is smaller than the degree in the denominator. So here's our example. The degree in the numerator of example 2 is a degree of 2. The degree in the denominator is a degree of 3. So it doesn't matter how many terms there are or what the leading coefficients are, your asymptote is always going to be y equal to 0. And y equal to 0 is a special horizontal line because it is also the x-axis. And then our last possibility is if the degree of f of x is greater than the degree of g of x. In other words, the numerator's degree is larger than the denominator's. So here's our example. I have a 4th degree polynomial in the numerator, a 3rd degree polynomial in the denominator. Because the one in the numerator's degree is larger than the one in the denominator, there is no horizontal asymptote for this rational function. Okay, so try to remember the information in this table to answer questions about horizontal asymptotes. But remember to state them in the form y equal to a number in these two cases, and in the third case, there is no horizontal asymptote. All right. So we want to find the horizontal and vertical asymptotes of this function. So we have 2x squared over x squared minus 2x minus 3. All right, so let's deal with the vertical one first. You pretty much oftentimes find the vertical asymptote by setting this equal to 0. So, which is the same thing we did to identify domain. So that in terms of the work that needs to be done, there's a lot of similarities here. So I can factor this polynomial. So this becomes x minus 3 and x plus 1. So I get two solutions, 3 and negative 1. But remember, those are not solutions to this equation. That's not only are those two numbers restrictions on the domain, they also happen to be the vertical asymptotes. 3 and negative 1 are the vertical asymptotes of this rational function. So you would state them as x equal to 3, that's a vertical line, and x equal to negative 1, that's another vertical line. So now let's talk about horizontal asymptotes. Remember, that's when you're taking your limit as x approaches infinity. So here my degrees are the same. They're both second degree polynomials. So when their degrees are the same, I just have to look at the ratio of their leading coefficients. So it's 2 over 1 because the coefficient of x squared in the denominator is 1. 2 over 1 is 2. So my horizontal asymptote is y equal to 2. Okay, so let's move on. We need to find the horizontal and vertical asymptotes of this function, g of x equal to 3x minus 1 over x squared minus 4. Again, if I start with the vertical, you take the denominator, set it equal to 0. Again, if I solve this with the square root method, you get two answers, plus or minus 2, which means I have two vertical asymptotes at negative 2 and 2. And graphically, when you're graphing these by hand, when you graph a rational function, you want to show your asymptotes as dotted lines. So you would have a dotted line at x equal to negative 2 and another one at positive 2. They would both be vertical. Then to find the horizontal asymptote, you have to take your limit as x approaches infinity of the function. So this is the third scenario that I explained. The second scenario that I explained in the table above. The degree in the numerator is 1. The degree in the denominator is 2. So when the degree in the numerator is smaller than the degree in the denominator, that limit equals 0. So y equal to 0 is your horizontal asymptote. And don't forget, y equal to 0 is also the x-axis. All right, here's one more. Find the horizontal and vertical asymptotes of 3x to the 5th over x cubed plus x squared. So we're going to first solve the denominator, set it equal to 0. That's what you have here. You can factor this, take out an x squared. You're left with x squared times x plus 1. So if you take each factor, set it equal to 0, you'll get two solutions, 0 and negative 1, which are in fact not solutions. They are vertical asymptotes. So again, you state your asymptotes, your vertical asymptotes as x equal to negative 1 and x equal to 0. All right, so now let's look at our horizontal asymptote. That's when you take the limit as x approaches infinity of your function. So that's the third scenario in the table above. The degree on top is bigger than the degree on the bottom. This has a degree of 5. This has a degree of 3. So when that's the case, the entire function goes to infinity. Infinity is not a finite number, therefore there is no horizontal asymptote. So what are x and y intercepts? So it's similar to what you've done with other types of functions, linear functions and quadratic functions. X-intercepts are points on the graph where the graph crosses the x-axis. Y-intercepts is where the graph crosses the y-axis. You may have both x and y intercepts in a rational function. You may have neither, or just one, just x-intercepts or just a y-intercept. So to find the x-intercept, you want to set the numerator equal to 0 and solve the equation. Because you're basically letting y equal 0, and so the only way that y will equal 0 is if the numerator equals 0. And if you get real number solutions, and those values are within the domain, then the solutions are x-intercepts. The y-intercept is easier to find because that's when you let x equal 0. And as long as 0 is in the domain, you can find the y-intercept. If 0 is not in the domain, you will not have a y-intercept. Okay, so let's do an example of x and y-intercepts. We want to find the x and y-intercepts of f of x equal to 2x plus 8 over 5x plus 1. So first let's find the x-intercept. Remember, that's when you take the numerator, set it equal to 0. So that's a linear function. Subtract 8 divided by 2. You get that x equals negative 4. So negative 4, 0 is the x-intercept. So to find the y-intercept, that's when you let x equal 0. And if I plug in 0, you get 8 over 1, which is 8. So your y-intercept is 0, 8. Okay. So let's look at this in terms of a graph. This is, again, remember, this is the parent function called a reciprocal function. And we want to state what the transformation is of the function that's given, which is the one below. Then we want to find domain and range and state the vertical and horizontal asymptotes. So y equal to 1 over x plus 4, that is a horizontal shift 4 units to the left. Because remember, I'm impacting x directly. It's not this, which is different. That would be a vertical shift. So it's shifting 4 units to the left, which means that my domain is all real numbers except negative 4. And why negative 4? Because my denominator equals 0 when x is negative 4. So we need to skip that. And your range, well, that's going to be all real numbers except for 0. Here's the graph that was provided. It basically looks like the reciprocal function just shifted 4 units to the left. And your range, remember, you always look from bottom to top with range. This goes from negative infinity all the way up to 0, and then from 0 all the way to infinity. So there's your range. I have a vertical asymptote at negative 4. That's where the function is undefined. And you can see that at negative 4, your graph is either approaching infinity or it's approaching negative infinity, depending on which side you're on of negative 4 of the vertical line. And your horizontal asymptote, well, that's as you can see here that it's getting closer and closer to the x-axis. So as x approaches infinity, your y is going to 0. As x approaches negative infinity, your y is also going to 0. So it has horizontal asymptote at y equal to 0. And then here I also showed you a little bit about the intercepts. It has no x-intercept. It is impossible to solve this equation because the only way this could equal 0 is if the numerator is 0, and the numerator is a constant, it's 1. So there is no x-intercept. But for the y-intercept, that's when you let x equal 0. So that's the work you see here. So 0, 1/4 is a y-intercept, which is the point that you see here on the graph. Okay, so that's it for rational functions. Give the homework a try. Good luck.